Welcome to the Explainer. All right, today we're going to build your complete toolkit for mastering Chapter 1, Real Numbers. We're going to turn what can be a pretty tough chapter into a really high-scoring opportunity for you.
So, get this. How can a couple of ancient ideas help you score full marks on one of the most common exam questions out there? Well, we're about to find out. We'll uncover how Euclid's algorithm and the fundamental theorem of arithmetic are pretty much the secret weapons you need for your board exams.
Okay, so here's our game plan for today. We'll start with the basics. What are real numbers? Then we're going to add 3 really powerful tools to your kit. After that, we'll put them to work on some actual exam problems and finish up with a super handy checklist.
All right, first things first, let's quickly lay the foundation. So, what are real numbers? Well, they pretty much include everything from your regular integers and fractions to those tricky irrational numbers like pi.
Think of them as kind of the raw materials for this whole chapter. You see them everywhere, right? When you're measuring temperature with integers or calculating square roots with those irrational numbers. So yeah, understanding them is absolutely the first step before we can get to the cool tools.
Okay, let's grab our first tool. Now, when you see a question pop up asking for the highest common factor, or HCF, of two really big numbers, this algorithm is going to be your absolute best friend.
Now, don't let that name intimidate you, okay? Euclid division lemma sounds super formal, but it's something you've known for years. It's just a fancy way of saying dividend equals divisor times quotient plus remainder. The really important word here, though, is unique. For any 2 numbers you pick, there's only one possible quotient and one possible remainder. That's it.
So, how does it actually work? It's a simple process, really. You take the bigger number, divide it by the smaller one, and you look at the remainder. Now, if that remainder is 0, awesome. The smaller number is your HCF. You're done. But if the remainder isn't 0, you just do it again. This time, you use the divisor and the remainder. You just keep repeating this whole thing until you finally hit a remainder of 0. And that divisor you used in that last step, boom, that's your HCF. All right, time for tool number 2. This one is all about breaking numbers down into their most basic parts. It's called the fundamental theorem of arithmetic, which, by the way, is also known as the unique factorization theorem. Pretty cool name, huh? And this is seriously powerful. What this theorem says is that every single composite number has its own unique prime fingerprint. Think about it like that. So for 360, it's 2 cubed times 3 squared times 5. No other number has that exact same combination of prime factors. And it's this uniqueness that makes it a total game changer for finding both the HCF and the LCM. So, what's the difference between finding the HCF and LCM with this method? It's all about what you're looking for. For the HCF, think of yourself as a detective. You're only interested in the prime factors the numbers have in common, and you take the smallest power of each one. But for the LCM, you're more like a collector. You want every single prime factor involved from all the numbers, and you grab the greatest power of each. It's a simple difference, but it's super important to get it right. And you absolutely cannot forget this key relationship. It's a total lifesaver, especially for those one-mark verification questions that pop up all the time. If you've just calculated the HCF and LCM, you can do a super quick check. Just multiply them together and see if it equals the product of your original 2 numbers. If it does, you know you nailed it. Okay, let's talk about a special technique now. This one often shows up as a 2 or even a 3-mark question, so it's worth paying attention. We are going to completely demystify how to prove a number is irrational. The whole thing is built on one single powerful idea. You're going to see this phrase a lot. It's basically the final knockout punch in every one of these proofs. The entire strategy, the whole method, hinges on this one amazing idea. It's called proof by contradiction. You start by assuming the exact opposite of what you're trying to prove, and then you show step by step that your assumption leads to something completely impossible, a contradiction. So here's your game plan, and you're going to use it every single time. Step 1, you assume the number, in this case 2 minus root 3, is actually rational. You're playing devil's advocate. From there, you just use some basic algebra to isolate the known irrational part, the root 3. What this does is it forces a logical showdown. You end up with a statement that says an irrational number is equal to a rational number, which we know is impossible. And that's it. That's the contradiction. You've proven your initial assumption was wrong, so the number must be irrational. All right, theory's done. It is time to open up that toolkit and actually use these tools on a real exam question. And we're starting with a high-frequency one, an absolute classic that you will definitely see. So prove that root 3 is an irrational number. This is one of the most fundamental proofs you need to know, period. It's a huge favorite for examiners. I mean, it appeared as recently as 2023. So let's walk through the solution step by step, exactly how you'd write it on your answer sheet. Okay, let's break this down. The slide lays out the whole logical chain. Look really closely at step 1. We start out by assuming root 3 is rational, meaning it can be written as a over b, where a and b are co-prime. Co-prime just means they don't share any common factors. Got it? But then, as we go through the steps, we prove that 3 divides a, and then we prove that 3 times also divides b. Wait a minute, that means a and b do have a common factor, the number 3. This completely contradicts our starting assumption that they were co-prime. See? That's the contradiction. It means our assumption was wrong all along, and therefore root 3 has to be irrational. Boom, proof complete. Whew, we have covered a lot of ground. So let's pull everything together and summarize your complete toolkit into one super powerful slide. This is perfect for that last-minute revision right before your exam. And here it is, your one-stop shop for real numbers. This little table connects every tool and concept directly to the kind of exam question it solves. And, super important, the number of marks it can get you. So you can use this to really focus your practice on the topics that are going to give you the biggest payoff. So now you have the toolkit, but what's next? Having the tools is really just the first step. The real key, the way you actually master this, is by practicing with them until using them becomes second nature. So go grab some past exam papers, start applying these methods, and build that confidence. That right there is your path to guaranteeing success.